This week we will study section 5.5, multiple angle identities. The objectives of this section is to use double, power reduced, and half angle identities to evaluate trigonometric expressions and to solve trigonometric equations. By letting alpha and beta both equals theta in each of the angles, some identities that we learned on the previous section, we can obtain the following double angle identities. Sine of 2 theta equals to sine of theta cosine of theta. For the cosine of 2 theta, we have three identities that when you apply them, you can use any one of them and you're going to have exactly the same results. One of them is, it says cosine of 2 theta equals cosine square of theta minus sine square of theta. The other one says the cosine of 2 theta equals 2 cosine square of theta minus 1. And the last identity, cosine of 2 theta equals 1 minus 2 sine square of theta. Also, we have a formula for the tangent of a double angle. Tangent of 2 theta equals 2 tangent of theta divided by 1 minus tangent square of theta. So let's start making an example. Evaluate expressions involving double angles. If sine of theta equals negative 7 over 12, on the interval 3 pi halves to 2 pi, we're going to find sine of 2 theta and cosine of 2 theta and tangent of 2 theta. So let's see how the solution goes. Since sine of theta equals y over r by the definition of the basic definition of sine of theta, that is opposite over adjacent, or y over r, sine of theta becomes equals, or is given, equals negative 7 over 12 on the interval 3 pi halves to 2 pi. And we have to determine one point of the terminal side of theta. And this point has y coordinate negative 7 and a distance from the origin to the point of 12 units, as is going to be shown in the diagram that we're going to start making it here. We draw the x-axis, we have the label the x-axis, the y-axis. Also, we know that the initial side is represents 0 degrees of the x. Then if we go counterclockwise in the y-axis, we label it with pi halves. We continue increasing each pi. So on the opposite side of the x, we have pi. Down the y-axis, we have 3 pi halves. And returning to x, we have 2 pi. And then let us plot the terminal side of this angle. We have a point on this terminal side. We just plot it on the one part of the opposite side, or the terminal side of this angle theta that we are going to generate. And this point, before we draw a triangle, a right triangle, this side is the opposite to theta. So this is the triangle that we have is a 90-degree triangle. The opposite side would be negative 7. The value there is 12. And so far we have the out of another pair associated with the point that we just plotted here. We have the y coordinate that is negative 7, but we don't know the value of the x. So the idea here is to find the value of the x. So this is my angle that we labeled theta. This angle that we generating here is an angle that is on the fourth quadrant. And we need to find the x coordinate. And to find the x value, or the x coordinate, we're going to use the Pythagorean theorem. As you can see this figure at the right, we have a right triangle that is formed, and the only side that we're missing is the value of the x, or the adjacent side. So to find the value of the x, we use the Pythagorean theorem directly, and this becomes x equals, applying the Pythagorean theorem, x equals to the square root of the value of the r minus the square root of the value of the y. So x becomes equals the square root of 12 squared minus negative 7 to the second power. Simplifying the expression inside of the radical, it becomes 95, and x equals the square root of 95. The square root of 95 cannot be simplified, it's not exact, so we leave it like that. Then we complete the x coordinate of the other pair that we have in here is the square root of 95, and the adjacent side of theta, it is square root of 95. Now we can find with this information, with the value of the x, we can find the cosine of theta, that is x over r, and the value of the x is the square root of 95, and the value of the r is 12. So the cosine of theta equals square root of 95 over 12. And the cosine in the fourth quadrant, so it makes sense what we have, it is positive. Positive square root of 95 over 12. Also, we can find the tangent. The tangent in the fourth quadrant is negative. Y is negative and the x is positive. So tangent is y over r and y over x. And the value of the tangent is negative 7 over 12. Tangent equals y over x, not y over r, is y over x. And the tangent will be negative 7 over 12. So we have so far what we need to find. This is what we need to, the information that we need to find in order to complete sine of 2 theta, cosine of 2 theta, and the tangent of 2 theta. Continue with example 1. We know that we just found that the cosine of theta is equals square root of 95 over 12, and the tangent of theta, it is negative 7 over 12. So we need these values in order to evaluate each one of the things that we are being asked for. Now let's use these values and the double angle identities for sine and cosine to find the sine of 2 theta and the cosine of 2 theta. And to find the tangent of 2 theta, we can use either the formula for the tangent of a double angle identity or the definition of tangent, but we can wait for that. So let's begin finding the sine of 2 theta. If you check the identity for the sine of 2 theta, the identity says that sine of 2 theta is equals 2 times sine of theta times the cosine of theta. We already know both values. The sine of theta is negative 7 over 12, and the cosine of theta is the square root of 95 over 12. So we replace all these values, and now what we need to do is to simplify this expression, and the answer becomes negative 7 square root of 95 over 12. How did I get this? If you notice, one of the ways of simplifying this is by, actually you can multiply 2 times 7, that it would be negative 14 square root of 195, or negative 14 over times the square root of 95 over 12 times 12, it would be 144. And then you can simplify the numbers, negative 14 over 144, and in simplest form it becomes negative 772. So the answer, and by using any way of simplifying the fractions, becomes negative 7 square root of 95 over 72. And now, how can we find the cosine of 2 theta? We have 3 probabilities for finding, or 3 possibilities for finding the cosine of 2 theta. One of the identities for the cosine of 2 theta is cosine square of theta minus sine square of theta. So we could have used that one. Another one is 1 minus 2 sine square of theta. And the other one, the one that we're going to use in here, just because I made the decision to use this one, it is 2 cosine square of theta minus 1. In this case, for the cosine of 2 theta, guys, you have 3 identities, and you can use any one of those. And the answer, it has to be exactly the same. So let's continue. Let's replace the cosine of theta that we know that is the square root of 95 over 12 into this identity, and it becomes this expression 2 times the square root of 95 over 12 to the second power minus 1. And we can simplify, we can rid of the we can raise to the second power the fraction, and it becomes 2 times the square root of 95 to the second power is, you can cancel the radical, and it becomes only 95 over 12 to the second power, that is 144. Then we need to simplify this expression. 2 times 95 over 144, it is the same as 95 minus 72 minus 1. What we can do in here, because we need to have the same denominator, is to express 1 like a fraction with the same least common denominator as 95 over 72. And this expression is 72 over 72. So 72 over 72 is 1, and it has what I needed, the same denominator, 72 minus over 72. Now that we have the same denominator, we can subtract. We keep the denominator, we subtract numerators, and 95 minus 72 becomes 23 over 72. And this is the cosine of 2 theta. And finally, tangent of 2 theta, we can use, like it was mentioned before, the double angle, the tangent for a double angle, or the definition of tangent. Remember the tangent in one of the basic identities that we studied in section 5.1, tangent of theta is equal sine of theta over cosine of theta. In here, since we have tangent of 2 theta, we can use tangent of 2 theta equals sine of 2 theta over cosine of 2 theta. And the good news is that in here we know what is the value of the sine of 2 theta and the cosine of 2 theta. So we just replace those values, and this becomes tangent of 2 theta equals sine of 2 theta, that is negative 7 square root 95 over 2, and the cosine of 2 theta, that is 23 over 72. In the next step, if you notice, this is a complex fraction. In the top we have a fraction whose denominator is 72, and at the bottom is also a fraction that has denominator 72. We can cancel the denominators because they are repeated, they are the same, so we can get rid of them. If you're going to use the euro operation, you can do it, but in here we're going to cancel these values, and this becomes equals negative 7 square root 95 over 23, and this will be the answer of the tangent of 2 theta. We will have obtained exactly the same result we should have used the identity tangent of 2 theta equals 2 tangent of theta over 1 minus tangent square of theta. Why we decide not to use this one? Because it would be a longer process that would lead us exactly the same answer. And here the only thing that we did was to replace the sine of 2 theta and the cosine of 2 theta to find the tangent of 2 theta. Let's make a second example. In example 2, we're going to solve an equation by using a double angle identity. So now we're going to see an example how to solve equations by using or applying a double angle identity. And here the equation is cosine. We're going to solve cosine of 2 theta equals sine of theta on the interval from 0 to 2 pi. And let's begin making the following. I know that the cosine of 2 theta has 3 probabilities for the identity. I mean, we have an identity, 3 identities for the cosine of 2 theta. And I need to choose the one that has sine involved in that identity. And the identity that it has only sine involved with it is the one that it says cosine of 2 theta equals 1 minus 2 sine square of theta. That's exactly the identity that I'm going to use in here. So instead of copying cosine of 2 theta, I replace it by the other side of the identity. That is says the cosine of 2 theta equals, that's what I'm going to use at this moment, 1 minus 2 sine square of theta. And I continue with my equation minus sine of theta equals 0. Now this is, if you notice, this is a quadratic equation where we have the function sine. So it's a quadratic equation. We need to arrange here, and it becomes negative. And I notice also is something that it can be done, that it can factor the negative sign of negative 2 sine square of theta. So it becomes negative, and I switch all the signs. It would be negative parenthesis 2 sine square of theta. The minus sine theta becomes plus sine of theta, and the 1 becomes minus 1 equals 0. Now I did this because it's a good idea to have the quadratic term of this expression that is like a quadratic expression positive. And then in the next step, I don't need the negative sign. The negative sign doesn't make any effect. It is like having negative 1. I need to get rid of it. It passes the other side dividing, so we don't need that. And the only expression that we need is 2 sine square of theta plus sine of theta minus 1 equals 0. And this equation, the left side of this equation can be solved by factoring. And this factoring, the factoring that I can use in here is the factoring for factoring the quadratic polynomial. So what I need in here is to use guessing or trial and error. And I notice that 2 sine of theta, 2 sine square of theta can be expressed like 2 sine of theta times sine of theta. And I need to take care of the constant, negative 1. Negative 1 can be expressed like negative 1 times 1 in this order. And then I multiply across to see this way of arranging the factors work. And when I multiply across 2 sine of theta times 1, it becomes 2 sine of theta. Negative 1 times sine of theta becomes negative sine of theta. And 2 sine of theta minus sine of theta equals sine of theta. That is exactly the term in between. That is a way to check that the factoring or the factors that I'm having in here are correct. Therefore, I continue. And the factors that I have are 2 sine of theta minus 1 times sine of theta plus 1. And this must be equal 0. Now, what I do at this point? At this point, I have 2 factors. And what I need to do is to set, by using the zero product property, each factor equals 0. So 2 sine of theta minus 1 equals 0, or sine of, and okay, let's begin solving the first one. 2 sine of theta minus 1 equals 0. Leaving alone the sine of theta, this becomes equals 1/2. And now what I need to do is to find the value of the angle. And you can use the unit circle at this point, or a table of angles, like the one that we used in the class before, and to figure it out for which angle the sine of theta is equals to 1/2. And actually we have two values for this. One that is in the first quadrant and another one that is in the second quadrant. And the values of theta are pi/6 and 5pi/6. Like I said, you can check these values, you can have your unit circle, and you can see that those values work. What it would be the solutions of the second equation, sine of theta plus 1 equals 0. I leave alone sine of theta becomes equals -1. Again, sine of which angle will give us -1. And checking in the unit circle, if you're using a calculator, theta will be equals 3pi/2. So the other angle that we have in here is 3pi/2. Therefore, the solution set of this equation becomes pi/6, 5/6, 3pi/2. Let's continue. We can use the double angle identities to obtain the identities that we're going to call them the power reducing identities. And what are the power reducing identities? The first one, it is sine square of theta that is equals 1 minus cosine of 2 theta over 2, cosine square of theta that is equal to 1 plus cosine of 2 theta over 2, and tangent square of theta equals 1 minus cosine of 2 theta over 1 plus cos of 2 theta. Notice that in these identities, we have the sine square of theta, for example. It is when we get the identity becomes equals to 1 minus cos of 2 theta. So the angle is double, 2 theta over 2. And the same happens with the other ones. Cosine square of theta equals to 1 plus cos of 2 theta over 2. And tangent square of theta, it becomes equals, it's like we put together sine square of theta over cosine square of theta, and we simplify it. And what we will get is 1 minus cos of 2 theta over 1 plus cos of 2 theta. Let's make an example where we can use a power reducing identity. In example 3, we're going to use an identity to reduce a power. So we're going to rewrite cosine to the 4th power of x in terms of an expression that has no powers greater than 1. So the idea is to get rid of the power form. How are we going to obtain this? Let's begin. First of all, if we have cosine to the 4th power of x, this is exactly the same as having cosine to the 2nd power of x raised to the 2nd power. This is by using powers of powers. That when we have powers of powers, we multiply the exponents. So cosine to the 4th power of x becomes equal to cosine square of x to the 2nd power. Then, in the next step, what we're going to do is to use one of the identities that we have for the power reducing. So we're gonna replace the cosine square of x by 1 minus cosine of 2x over 2. That's one of the identities and the power reducing identities that you can check. Cosine square of x is equal 1 plus cosine of 2x divided by 2. And all this whole expression raised to a 2nd power. Now in the next step, what we're going to do is to expand both sides, the top and the bottom, to the 2nd power. If we expand 1 plus cosine of 2x to the 2nd power, rather by using multiplication of FOIL or a special product, the top becomes 1, let me use the special product. 1 to the 2nd power will be 1, then to obtain the term in the middle, we multiply 1 times cosine of 2x and multiply by 2. It will be 2 times cosine of 2x plus the square of the last term, cosine of 2x, that it will be cosine square of x, cosine to the 2nd power of 2x, over 2 to the 2nd power, that becomes 4. So here what we did was to multiply. Then, in the next step, once again, I can use to replace cosine square of 2x the power reducing identity. In this case, I'm going to use it with the argument 2x. So I continue with the simplification. This becomes 1 plus 2 cosine of 2x plus, instead of copying cosine square of 2x, I'm going to copy 1 plus cos of 4x over 2. This is by using a power reducing identity for the cosine over 4. Then I notice that in the top I have addition of 1 plus 2 cosine of 2x plus 1 plus cosine of 4x over 2. It is really important to have a same denominator, so what I can do in the next step is to get a common denominator. Also, I noticed that since the whole expression is being divided by 4, I can take care of this by taking it out. Dividing by 4 is equivalent to multiply by 1/4, so this will be 1/4 times. Like I said, I need to create a least common denominator. And what I can do in here is to multiply the expression 1 plus 2 cosine of 2x by 2 and divide by 2. This would make it, it will let us to have a common denominator 2, as I have it for 1 plus cosine of 4x over 2. So this becomes equals 1 over 4 times, when I multiply by the 2, the expression in parentheses, it becomes 2 times 1, it will be 2. 2 times 2 is 2 cosine of x. X is 4 cosine of 2x plus 1 plus cosine of 4x. That is the expression that has the denominator 2. And all this is over 2. And finally, I don't know, you notice that the power 4 has been eliminated since the beginning. That's what we needed. And the only thing that I have to do in here is to combine like terms at the top. The 2 in the bottom can be multiplied with the 4 outside. It will be 1/8. And this becomes 1/8 times. Simplify the expressions inside. 2 plus 1, it will be 3 plus 4 cosine of 2x plus the cosine of 4x. And we just get what we needed, that was to get rid of the power 4 and express it with an expression that has no power greater than, no powers greater than 1. Let's make a new example. An example 4, we're going to use an equation using a power reducing identity. And in this case, the equation given is 1 minus sine squared of theta minus cosine of 2 theta equals 1/2. And we're going to make a replacement for the expression in red, sine squared of theta. So we're going to need to use an identity. And the identity that we're going to use, it is the one that it says that sine squared of theta is equal 1 minus cosine of 2 theta divided by 2. So we replace in the original equation this expression, and it becomes 1 minus cosine of 2 theta over 2 minus cosine of 2 theta equals 1/2. Then what I can do is, since I have I notice that I have denominators on both sides, it is and the denominator that I have in common in both sides is 2. What I can do to clear out these denominators is to multiply everything by 2. So I multiply the left side by 2 and the right side by 2. When I simplify this expression, this becomes 2. I use the distributive property. 2 times 1, it will be 2. And I multiply 2 by the 1 inside of the brackets. So it's 2 times 1 is 2. Minus 2 times the expression in parentheses. I just leave it indicated at this point. 2 times 1 minus cosine of 2 theta over 2 equals, and at the right side, 1/2 times 2 is 1. Then I notice that I can cancel these 2's over here. And the expression becomes 2 minus, and I use the distributive property with the sign in front of the parentheses. Negative times positive 1 is negative 1, and negative 1 times negative cosine of 2 theta becomes cosine of 2 theta equals 1. 2 minus 1 is 1 on the left side, plus cosine of 2 theta equals 1. And leaving alone the cosine of 2 theta equals, it will be cosine of 2 theta equals 0. 1 minus 1 is 0. And then at this point, what we need to do is to find the value of theta. And we're going to notice that the following at this point. We need to leave the argument, that is 2 theta. We're finding the cosine of 2 theta alone. So in here, by using the way that we use the calculator, actually, it is 2 theta will be equals the inverse cosine. How can I find the measure of the value of the 2 theta? Because that's the expression that we're taking the cosine for. So 2 theta becomes equals the cosine, the inverse cosine of 0. So when you evaluate the cosine inverse of 0, and you're looking for the angle whose value is 0 for the cosine, the inverse cosine of 0, the value is 0, it will be 2 theta equals the angle for which the cosine is equal 0 is pi halves, but also 3 pi halves. So 2 theta becomes, and you can use the unit circle to check this, 2 theta becomes equals pi halves or 3 pi halves. But we have an issue in here that actually what we need is not the value of 2 theta. What we need is the measure of theta. So what we need to do is to get rid of the 2. It passes the other side, dividing, or to leave it alone, you can multiply both sides by 1/2, and it becomes that what we're finding here is that theta becomes equals pi over 4, or theta equals 3 pi fourths. The 2 that is multiplying passes dividing on the other side. So theta becomes pi fourths, or 3 pi fourths. And this is what we call particular solutions, or punctual solutions. This will be the solutions on the interval from 0 to 2 pi. And this exercise, notice that when they say solve an equation, they don't mention that you need to find the solutions on the interval from 0 to 2 pi. So when that is the instruction, what we need to do is to find not only the particular solutions that are the ones that we just found, but also the general solutions. So what will be the general solutions? The general solutions will be like this. What I need to do is to add to, for example, theta equals pi fourths, a multiple of the period of this function cosine of 2 theta. Cosine of 2 theta, the period, to find the formula to find the period of cosine, remember there is 2 pi over b, and the value of the b in here is 2. So 2 pi divided by 2 will give us pi. So to find the general solutions, it will be theta equals pi fourths plus n times the period, or 3 pi fourths plus n times the period. But we just remember how to find the period. The period is pi. So the general solutions is the following. Theta equals pi fourths plus n pi, or 3 pi fourths plus n pi. Why n? N represents an integer, and the n could be positive or negative, representing that you can find as many solutions as you want. Remember that the cosine is a periodic function, and when you graph it, you remember that the graph has a period, or for example in this case pi, and when you graph it, you can graph as many as you want. So the same happens when you find the solutions. In general, the cosine of 2 theta, and in this case that is equals 0, you can have several values, and to find those several values, what you need to do is to find the general solutions. And this is the solution of this exercise. By replacing theta by theta over 2 in each of the power reducing identities, we can derive each of the following half angle identities. Let's see the half angle identities. Sine of theta divided by 2 is equals plus minus the square root of 1 minus cosine of theta divided by 2. Cosine of theta over 2 equals plus minus the square root of 1 plus cosine of theta divided by 2. And for the tangent of theta divided by 2, we have the three identities. Tangent half of an angle equals plus minus the square root of 1 minus cosine of theta over 1 plus cosine of theta. Another one that it can be used, tangent half of an angle equals 1 minus cosine of theta over sine of theta. And the last for these identities, tangent of theta divided by 2 equals cosine of theta over 1 plus sine of theta. And these are the identities that we can use. Notice that in some cases, in sine of theta over 2, for example, the cosine half of an angle, and the first one of the tangent half of an angle, we have a plus minus sign in front of a radical symbol. Sometimes, depending on the position of the angle theta, we're going to use a positive, a square root of the expression inside, of a negative of the expression inside. Let's make an example where we can evaluate an expression that involves half an angle. Find the exact value of the cosine of 105. The solution goes like this. We know that 105 is the same as 210 divided by 2. So we can use the half angle formula for the cosine of theta divided by 2. Cosine of theta divided by 2 is equal to 1 plus cosine of theta divided by 2. That's the identity that we're going to use. And in this case, the value of the angle theta is 210. So what sign should we use when we apply the formula for the cosine and half of an angle? Because 105 is an angle that is in the second quadrant, and in the second quadrant only the sine and the cosecant are positive, the cosine of 105 will be negative. Those we will use the negative sign in half in the half angle formula. So cosine of 105 is the same as the cosine of 210 divided by 2. And by using the identity of the cosine of half of an angle, this equals negative, because remember what we said about the angle theta that is in the second quadrant, equals negative the square root of 1 plus cosine of 210, and this expression divided by 2. Now, the cosine of 210, it's an angle that is located in the third quadrant. And the cosine of an angle in the third quadrant is negative. Now, how can I know the exact value of the cosine of 210? 210, it's a multiple of 30 degrees. And we know by looking at the spatial table that we used before for the angles, the table for the spatial angles, 30, 60, 90, that the cosine of 30, it is square root of 3 over 2. But since the cosine is negative in the third quadrant, it would be negative. The cosine of 210 would be negative square root of 3 over 2. So this expression becomes equals negative the square root of 1 minus, replacing cosine of 210 plus negative, that becomes negative. So 1 minus square root of 3 over 2, everything divided by 2. Now I have to simplify the numerator, so I need to create a same denominator. 1 is the same as 2 over 2 minus square root of 3 over 2. So now I have at the top the same denominator. And when I simplify that expression at the top, it becomes negative square root of, at the top, the numerator, 2 minus square root of 3 over 2, and everything over 2. Then I need to simplify this. I can use evaporation, and this becomes negative square root of, at the top, 2 minus square root of 3 over 4. Then I can use the quotient of radicals, and this becomes negative the square root of the expression at the top, that is 2 minus square root of 3, so it remains like that, over the square root of 4. And the expression at the top is a really complex expression, so we cannot do anything else, so we leave it like that. And we simplify the denominator, the square root of 4, it is 2. So the answer to this expression, it is negative square root of 2 minus square root of 3 divided by 2. Therefore, the cosine of 105 is equals negative square root of 2 minus square root of 3 divided by 2. Now let's make an example where we can solve an equation by using a half angle identity. So let's solve the equation cosine square of x equals sine square of x divided by 2. We're going to make a substitution for the expression sine square of x over 2, and my equation becomes cosine square of x equals sine of x over 2, and this expression raised to the second power. Now, this expression in red can be replaced by the half angle identity for the sine, and this becomes the equation cosine square of x equals, replacing sine of half of an angle by the right side of the identity, it would be equals, the cosine square of x equals plus minus the square root of 1 minus cosine of x divided by 2, and the whole expression raised to a second power. This expression that it contains a radical, when we raise it to a second power in the plus minus, disappear, the plus minus becomes positive and the radical symbol disappears. So the cosine square of x becomes equals 1 minus cos of x divided by 2. I get rid of this division, it passes to the other side multiplying, so my equation now it is 2 cosine square of x equals 1 minus cosine of x. And this is a quadratic equation. I need to make one side equal 0, and when I make it equal 0, my equation now it is 2 cosine square of x plus cosine of x minus 1 equals 0. And I need to factor this equation. I can use the guessing or trial and error method. I need to find the possible factors of 2 cosine square of x. There are 2 cos of x and cos of x, and I do the same with the negative 1 and 1 in that order is going to work. I multiply across, and when I multiply across 2 times 2 cosine of x times 1 and cosine of x times negative 1, it gives us 2 cosine of x minus 1 minus cosine of x equals cosine of x, that is the term in the middle, meaning that the factors that the way that I factor the trinomial or the equation 2 cosine square of x plus cosine of x minus 1, it's correct. So my factors 2 cosine of x minus 1 and cosine of x plus 1. I put them together, multiplying, and I make my equation once again equals 0. Now I need to set each of these factors equals 0. 2 cosine of x minus 1 equals 0. The other factor, cosine of x plus 1, also equals 0. Let me solve the left side equation, and it becomes that the cosine of x equals 1/2. For what value of x, for which angle, the cosine of that angle is equals 1/2. The cosine is positive in 2 quadrants, and the first one in the 4th quadrant. So what are the angles? It is pi over 3, that's in the first quadrant, and the other angle in the 4th quadrant, it will be 5 pi over 3. So the values of the x are pi over 3, 5 pi over 3. You can check these values in the unit circle. And solving the other equation, cosine of x equals -1, for which angle the cosine of that angle equals -1. The value of the x must be pi. Cosine of pi, it will be -1. And these are the particular solutions. Remember that when in the equation, when you need to solve it, it doesn't mention anything about the interval that you need to solve this. What they meant is that you need to find not only the particular solutions, also you need to find the general solutions. And to find the general solutions, to each of these values, you're going to add a multiple of the period. So what is the period of the cosine of x? If when you have the cosine of x is the same as cosine of 1x, the value of the b is 1. The period of the cosine is 2 pi divided by b. b is 1, so 2 pi divided by 1, it would be 2 pi. So the period of this function is 2 pi. So the general solutions becomes x equals, for example, pi over 3 plus the period times n. So x will be equals 2 pi, or pi over 3 plus 2 pi times n, the period times n. That is the same as pi over 3 plus 2n pi. The second, it will be 5 pi over 3 plus the period times n, 2 pi n. And the last one, it will be, the last general solution will be pi plus the period of the function times n. So pi plus 2 pi n. And these are the expressions for the general solutions I will expect.